Friends, let's get started. To graph this guy, I think I'll just kind of make a wide scale there for the y-axis, and then okay. So let's go ahead and just graph this thing. So we only care about really what happens from 1 to infinity. So when you plug 1 in, you get 1. When you plug 2 in, you get, what would that be? 1/8, 3 1/27, 4 1/81st. I don't know, how do you say that? 1 out of 81. Anyway, 5 would be 1 out of 125. So you can see that this graph approaches 0 very, very quickly. Okay, and so the part of this graph that would be represented by this integral would be the bounded area there. So the goal for this lesson, my friends, is to form a connection between what an improper integral would do as far as whether it converges or diverges, and what its related infinite sum would do. And so basically, there is a connection between the integral from 1 to infinity of 1 over x cubed dx and the sum as n goes from 1 to infinity of 1 over n cubed. And so, and really, I guess, spoiler alert, we're going to find that whatever the improper integral does, the related sum will do the same thing as far as converge and diverge. So anyway, so we'll come back to this in just a little bit. Okay, so getting started here. Let's talk about the integral test. We'll talk about it on a theoretical level here. Actually, okay. So first, let's make sure you're okay with the argument behind it. There are conditions that your function rule that you're dealing with would have to meet. And so here are the conditions. If your function f is positive, continuous, and decreasing basically on the interval that you're of interest. And so for these problems, the interval of interest would be from 1 to infinity. So really quick, let's just look back at this example over here. Notice that this function rule is positive, meaning it's above the x-axis. It is continuous, meaning it doesn't have any basically vertical asymptotes. And it is decreasing. As it goes to the right, the graph continues to go down ever so gradually at the end, but it is decreasing for the entire interval from 1 to infinity. Okay, so if you're dealing with a function rule that satisfies those three things, then the idea is that the sum as n goes from 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx, where a sub n would be f of n. So I'm basically saying that, like, the function rules would be the same if we were using the same letters, okay? And so I'm going to go ahead and say like what the result is, and then we'll give the argument, okay? So the argument is that they either both converge or both diverge. So whatever the improper integral does, the related sum will do the same thing. Okay, so now let's talk about the argument behind it. And I'm not going to do this in a formal proof way, but this would be the idea behind a formal proof, okay? So remember that the conditions are basically that your graph has to look like this. Like, your graph has to be positive, has to be continuous, and it has to be decreasing on the interval from 1 to infinity. And I'm going to go ahead and label these values here. Okay, so first let's argue that they would both diverge together. So let's say that the integral from 1 to infinity of this function, let's say it diverges to infinity. Okay. Then what I'd like for you to look at is the fact that then the sum as n goes from 1 to infinity of a sub n, assuming a sub n and f of n would be the same. So let's look at this. So the sum as n goes from 1 to infinity of a sub n. How does that compare to the integral? Well, the integral would be all the area underneath the curve, right? And so if that area adds up to infinity, now let's look at what the sum as n goes from 1 to infinity of a sub n means. Well, that would be, so here's a rectangle of area a sub 1. And here's a rectangle of area a sub 2. And here's a rectangle of area a sub 3, a sub 4, a sub 5, a sub 6, etc. So I hope it makes sense that the sum, the related sum, can be shown that it is greater than or equal to the integral from 1 to infinity of f of x dx. And so, so the conclusion would be that the sum as n goes from 1 to infinity of a sub n will also diverge. There we go. So that's the argument that if the improper integral diverges to infinity, then its related sum would as well. Now let's look at the other argument. So a similar picture. So your function rule has to be positive, continuous, and decreasing. So now let's say the integral from 1 to infinity of f of x dx converges. Well, what would that mean if it converges? Whoops. Well, that would mean that the bounded area adds up to something finite, right? So that is that the integral from 1 to infinity of f of x dx is equal to something finite, right? Well, now let's look at the sum as n goes from 1 to infinity of a sub n, where a sub n is basically just f of x. So let's look at that. So let's put some markers in here so we have some things to compare. Okay, so there's a different way to look at the sum of all these values. So here it is. This rectangle right here could represent a sub 1. And this rectangle right here could represent a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and so on. Okay, so what do we notice? The sum as n goes from, maybe I should change that to say 2. The sum as n goes from 2 to infinity of a sub n would definitely be less than or equal to the integral from 1 to infinity of f of x dx. And since this is something finite, then this would also be finite. And I know that I did leave out what you'd get for the first term, but because your function was continuous, your first term is definitely something finite. And so if the sum as n goes from 2 to infinity of a sub n, if this is finite, then when you add in that little first term, which is this little rectangle right here, then you're adding in something finite. And that would give you the sum as n goes from 1 to infinity of a sub n, and it would be finite, since a finite number plus a finite number is a finite number. And so there's the argument. So we'll just say, therefore, there's the argument that if the improper integral converges, then the related sum will also converge. Oh my goodness, isn't that fun? Okay, so, and it's easy to remember, right? Whatever the integral does, the sum does as well. Okay, so if you were to come over here to the warm-up, we could talk about, you know, what did we know about this improper integral, right? Well, we knew that the improper integral, we've shown in the past that this converges, and we have methods. We'll review them today. But we could say that the integral from 1 to infinity of 1 over x cubed dx, that it does converge. And then we could say that its related sum would also converge by the integral test. So here's how that would look. The integral from 1 to infinity of 1 over x cubed, remember how to handle improper integrals, would be the limit as b approaches infinity of the integral from 1 to b of x to the negative 3 dx. And then we'll do antiderivative. So add 1 to the exponent, we'd get x to the negative 2, divide by the results. Whoops, I forgot my limit in front. Okay, you could plug in b. You could plug in 1. And then you could let the remaining b go to infinity, and notice that this first fraction would go to 0. And so you'd get 1/2. And so what did we just find out? We just found out that, therefore, the integral from 1 to infinity of 1 over x cubed dx, it converges. If somebody asked what it converges to, we could say it converges to 1/2. Really, the important part is that it converges, however. And then we could say, and by the integral test, remember that it's going to be really important that you can not just say converges or diverges, but you can say why. What test did you use? And you can give a decent argument. So by the integral test, we could say that the sum as n goes from 1 to infinity of 1 over x cubed also converges. Now, I wouldn't say that it converges to 1/2, though. So they don't especially converge to the same thing. So luckily, we're not going to be asked what that sum converges to. We'll just be asked if it converges or diverges. There you go. So that's what an integral test problem looks like. And with that said, I would love for you to do your best with example 1. The directions are for you to use the integral test to determine whether each series converges or diverges. In the next video, I'll show you kind of a formulaic way to show your work and write your answers, but I'd have you at least scratch out your scratch work and see how far you can get with these problems, and then check in with me.